Good morning. My name is Dr. Evan Tanner. I'm an assistant professor in the Meadows Endowed Chair of Semi-Arid Land Ecology here at the Caesar Kleberg Wildlife Research Institute. I really appreciate you all joining us this morning, and I'm very excited to talk to you today about temperature and about the implications of the thermal environment for deer management. So, as ecologists, as wildlife managers, we're all interested in really understanding two basic problems in ecology: what influences the distributions and what influences the abundance of organisms. Really, everything we do comes down to these two key tenets in both direct and indirect ways. And really, to understand that both the distribution and the abundance of a species, we need to know, both the resources that it requires, as well as the effects of environmental conditions on both those resources, resource availability, as well as direct implications and impacts on the species of concern. And so today I'm going to highlight this idea of the effects of environmental conditions, specifically temperature as an environmental condition. So in natural landscapes and even in unnatural, human-influenced landscapes, these landscapes act as thermal moderators. And what I mean when I say thermal moderator is that they are acting as a filter on temperatures and the temperatures that are available for organisms to utilize. So when we think about thermal conditions in landscapes, they're both structured by ultimate and proximate forces. Ultimate forces would be something like your geographic location, your latitude and longitude on Earth, as well as the prevailing climatic patterns. Whereas proximate forces are going to be more local. And so when we think about proximate forces and how they influence near surface temperatures, we can think about things like vegetation type, vegetation structure and cover, soil types that drive vegetation patterns, topographic features, and even disturbance events and land use patterns. All of these things are local proximate forces that influence the thermal landscape. And so we can take two fundamentally different landscapes here on the right side and look at the top and think that proximate forces driving thermal conditions here may be related to vegetation, but also to topographic features and soil types, and we'll get a resulting thermal landscape that looks like this. Whereas on the bottom, we can get a fundamentally different thermal landscape that's driven by different proximate patterns. This is a shinnery oak system, and so it has frequent fire disturbance. And so rather than things like topographic features, we may see a fundamentally different thermal landscape that's driven by different proximate forces, such as these fire events. So when we think about landscapes as thermal moderators, really temperature is a filter which can constrain the available environment for all living organisms. And so we have this schematic where we think about these ultimate forces, like where we're at on the landscape, climate patterns, and the variability of these ultimate forces that then drive not only soil types, management, vegetation types, disturbance events. These all filter into these thermal filters that dictate what environment is available to the organism. And of course, once we have the thermal environment that's available to the organism, we would expect that there are both direct and indirect effects that influence the organism's behavior, the organism's physiology, and then ultimately the reproduction and survival and population level parameters for these organisms. So for this first part, I'm going to focus on this top schematic, okay? And we're going to really take a deep dive into how vegetation and heterogeneity in landscapes drives thermal patterns. So if we think about a range of thermal conditions, all the way from the coldest thermal condition to the hottest thermal condition that can exist at a certain point on Earth, we can take a theoretical landscape, which is this gridded square down here, and we have a representation of usable space, space that is available to an organism and that is being selected by an organism, represented in the green, whereas white squares are representative of areas that are no longer usable because the thermal conditions aren't conducive for use there. And so as we transition from these very cold periods that may have very little space available for an organism. We can see that as we get to more moderate conditions, that landscape would predictably open up and be more usable. And then, of course, we would get a decrease again at the hottest periods, but it may be fundamentally different than those that are being used at the cold. Even though we could have the same percentage of usable space in the same landscape, we may predict that because changes in structure or species, that maybe hot areas are down here on the lower right, whereas colder areas perhaps are in the upper left with some overlap in between. And so how do we really quantify this? Well, one way we do this is by looking at something called operative temperature or black globe temperature. What operative temperature is essentially a measure of temperature for a black body. So a black body is, of course, a perfect absorber of radiant energy, and so it incorporates things like radiant heat from solar radiation, convective heating and cooling related to the wind, and of course the influence of ambient temperature. And so it's really important to understand how operative temperature and ambient temperature, or just air temperature here, is related, because we look at a weather station and we say, okay, it's 75 degrees outside or it's 95 degrees outside. And at a weather station, that's true, but ambient temperature is often measured with a solar shield. So it's protected from direct solar radiation, and it's not truly a measure of what an organism would experience on the landscape. So we can take, for instance, on this right side, let's look at the ambient temperature at 35 degrees Celsius. And we can see that at that moment, there is a predicted range of temperatures in the operative temperature variable that we would expect an organism to experience based on where they're at on the landscape. Okay, so again, we're looking at a weather station saying it's 35 degrees Celsius, but in reality, across a natural landscape, we could expect the range to be anywhere from maybe 30 degrees Celsius, so actually cooler, all the way up to almost 70 degrees Celsius. And once you get up into these temperatures, above 50 degrees Celsius, you're experiencing temperatures that are hot enough to denature proteins. So this is not just semantics. And so what we can do is take these black body temperatures and start to model what the landscape looks like based on things like vegetation cover, aspect, slope, and then take ambient temperature conditions and relate it back to the variability of operative temperatures on a landscape. So here you can see the same exact landscape, and as we transition from 24 degrees Celsius up to 42 degrees Celsius, you can see this variability in colors relating to different temperature ranges. And so at any given ambient temperature, there is a plethora of different operative temperatures that are available to organisms, and you can see possibly some overlap there where there's thermal refuge that's consistent across ambient temperatures, but of course we get that ebb and flow as thermal properties change. So again, you can kind of see this consistent relationship here between ambient and operative temperature that is generally a positive relationship, but also has a lot of variability. And so we can take this shape of this relationship and think about it from a theoretical perspective. So again, here we have this positive relationship with variability, and we have two different landscapes: a homogeneous landscape, so a landscape with not a lot of changes in vegetation cover, and then we have a heterogeneous landscape, a landscape that's got maybe a lot of disturbance, a lot of management, variability in cover types and structure. And I want to point out these two horizontal dashed lines, which represent the thermal tolerance of an organism. So we can think about the lowest temperature that they will tolerate and the highest temperature that they will tolerate. And then we can also look at these diagonal red lines and think about this as the thermal environment that's available for organisms. And so as we move from a homogeneous landscape that has potentially fewer thermal options, we have this shaded region here that is truly what is usable by the organism, because it matches where the thermal tolerance is and where the thermal environment allows that organism to be. However, if we increase thermal heterogeneity and we increase the thermal options within this landscape, what we can see is that the available space for an organism is now vastly increased. So this is just kind of a theoretical explanation of how heterogeneity can increase choices for organisms. So what we can do is look at different landscapes with varying levels of vegetation heterogeneity, and we can see measure the thermal options on those landscapes and see that areas with high and medium levels of vegetation heterogeneity have not only greater ranges of temperatures throughout the day, but also on the bottom we have the standard deviation of temperatures, and we can see that variability of these thermal options are greater in areas with high and medium levels of vegetation heterogeneity. Basically meaning that heterogeneity means more thermal options for organisms in those landscapes. We can look at species-specific or vegetation cover-specific options and see, things like forest cover and the range and temperatures across the day under a forest are much different than under shinnery oaks or salt cedar or even hybrid shinnery oaks. So again, we can get it down to species-specific variability, and we know that species matter when it comes to buffering thermal options. One way we can do this is look at how solar radiation is mediated by vegetation structure. And so on this graph here, we have different colors representing different vegetation types, the green being closed canopy cedar, the yellow being grassland, and the red being bare ground. And we can see that this is variance in temperature, so variability in thermal options across these different vegetation types. And you can see quite a bit of range, but we were able to quantify the changes in these thermal conditions during the 2017 total solar eclipse. And so what we did is actually use that eclipse to remove most of the solar radiation from the system, and as you can see, that variability at the peak of the eclipse completely homogenizes. And this really represents the importance of solar radiation in understanding thermal landscapes for organisms. Again, ambient temperature alone is not telling the whole story. It's really important also to understand how energy and thermal energy is transferred between these systems. You can think about a grassland down here in South Texas at night, and the grass area is going to emit certain long waves of radiation back into the atmosphere. Of course, under a tree canopy, that radiation would be, some of it would be re-reflected back down to the ground. And of course, the vegetation itself has its own thermal characteristics, so it's going to be sending radiation back down to the ground. And so this really explains why at night, on a clear night, the area under a tree canopy is actually warmer than the cooler areas outside of the grasslands. So again, there's a lot of complexity to understanding these systems, and really the take home is that you can have similar vegetation structure, but you can have drastically different thermal characteristics. So if you think about something like a sand sagebrush versus a aromatic sumac, you may say, okay, they may be functioning similar on the landscape, but because there's species-specific differences, like differences in reflectance of light, absorption of light, transmittance of light, wind permeability, all these things are gonna cause species-specific differences in thermal options for organisms. Okay, so can we mitigate for temperature with management? And the answer is, of course, yes. We are now starting to build really nice complex models that look at things like vegetation composition, so the percent of grass for litter, bare ground, and shrub within a system, the vegetation structure, such as overhead obstruction, vegetation height, and even vegetation diversity, so species richness. And we're starting to build structural equation models that actually explain the direct positive and negative relationships that ultimately drive these temperatures that we're measuring. This is with an I button, but it could be any temperature measurement. And so here we have blue lines that have positive relationships. So percent shrub has a positive relationship with overhead obstruction, which then has a negative relationship with temperature, meaning that there would be cooler temperatures with increased overhead obstruction and percent shrub cover. So knowing these relationships can really help us understand what our management is going to do to the landscape. And the important thing to understand again is that not all cover is created equally. Here we can have 4 different levels of ambient conditions, and the black areas on this landscape represent areas that are thermally suitable, so areas that an organism would select during a given ambient temperature. And you can see that as you transition from really hot periods here at A to moderate conditions, the amount of usable space actually opens up quite a bit more. And then as we get to really cold conditions, you can see that it decreases again, and that that areas that are selected for during really cold temperatures might not coincide with those selected at very high temperatures. Okay, and so this really emphasizes this variability in species composition, that not all structure is the same, and that cover is not just cover, and it's not just about avoiding predation. It's actually about thermal selection. So this habitat is actually more of a fluid concept. Okay, so we talked about the top box, about how management, disturbance, soils, vegetation all influence the environment that's available for an organism. Let's dive into species like the white-tailed deer and think about how the environment that's available to an organism is influencing the organism's behavior, the organism's physiology, and then ultimately the reproduction and survival that translates to population characteristics. And so when we think about how the environment is influencing these subjects, we can think about two ways. It could be a direct effect or an indirect effect of temperature. And the first thing I'm going to do is cover direct effects. So in physiology, we think about things like thermal performance curves. And really what these are is just a way to understand how an organism is going to perform at given temperatures. And really the important thing here is we have temperatures called CT min, so critical thermal minimum and critical thermal maximum. Ultimately what these are is the coldest temperature and the hottest temperature that an organism can perform theoretically without perishing. And so that's its thermal tolerance range between those two values. And then we also have what's called a temperature optimum. And that is the optimum temperature that it is performing in a thermally safe margin. And so one of the ways we measure performance is metrics like metabolic rate. And so, researchers have looked at this with white-tailed deer in the past. This is actually measurements of increases in metabolic rate as prevailing temperatures decrease below their critical thermal minimum. And so this linear relationship you see as you decrease in temperatures is representative of increased metabolic rates relating to those colder temperatures. And what's really interesting about this is that we see that this relationship actually varies whether or not it's the summer, winter, or spring. So a lot of these performance metrics are dynamic. We can think about it in relation to direct effects on reproduction. We know that gestation actually increases fasting metabolic rate of white-tailed deer, and so that is represented by this curve here, and the dashed line is actually representative of fasting metabolic rate for non-pregnant white-tailed deer. And so you can see that as you increase in days of gestation, we actually see this increased fasting metabolic rate, which could have translate to potentially increased heat in the gestating female, and potentially thermal consequences unless certain options are selected on the landscape. We know that thermal conditions can directly impact survival and mortality. This has been shown in things called ecological pinch points, where as you decrease or increase in certain extreme temperatures, we see a subsequent decrease in usable space, but also a decrease in survivorship. These are actually hazard ratios. So as you decrease in this line, you're actually getting increased survival. It's a little counterintuitive, but the higher the value of the hazard ratio, the lower survival. And when I was thinking about deer for this presentation, we just had this giant winter storm Uri in Texas, and some of the stories that circulated throughout social media and other media was these mass die-offs of axis deer. So I think this is actually a really good example of how these thermal conditions can pinch an animal into spaces that may not be thermally suitable anymore, and end up in mass die-offs of these organisms. Another direct effect is how organisms are using their space. This is some data from Jacob Dykes, PhD student here at CKWRI, and he is using experimental pens during extremely hot periods of the summer to see how deer are selecting different levels of shade, varying from no shade all the way up to 90% shade. And what's interesting about these relationships on the y-axis is basically the selection of these sites, is that not all shade is made equally. When we look at the control, the 30% and the 60% shade, we can see that obviously the intercept of this relationship varies. 60% has a little bit higher selection on these moderate temperatures, but the relationship, the slope, is similar. Whereas as you transition to 90% shade, that slope is fundamentally and functionally different. And so we're seeing thresholds of where certain amounts of shade matter, and you can translate that to perhaps canopy cover of woody species for these organisms. Other direct effects can relate to movement. There's studies that show that as we increase and decrease in temperature extremes throughout the year, this is different seasons of the year, these different lines, we can see that the percent of the day that that white-tailed deer are active and the percent of time that they're active within 3-hour intervals decreases. So their movements are decreasing significantly as temperatures get extremely cold and extremely hot. Finally, there's new data that shows that direct effects of temperature can influence feeding activity. There's an experiment that shaded feeding troughs and then had unshaded feeding troughs, and what they found was that not only is the feeding activity influenced by this shade and these decreases in thermal conditions underneath the shaded feeding troughs. This is shown by this black line where you can see during the hottest period of the day there's more activity, feeding activity, compared to the dashed line, which was unshaded feeding troughs. But this also translates to differences in consumption of food. We can see that the kilograms of feed per deer per day was significantly higher in the shaded feeding troughs versus the unshaded feeding areas. So those are some examples of direct effects of how temperature influences not only the physiology of deer, but also the space use, movement, and feeding activities of deer. But there's also this impact of indirect effects of temperature on deer, and this is an area of research that is a little bit more difficult to address and also has not received as much attention because it is difficult and complex. Some suggestions in previous research have thought that shifts in feeding behavior of deer due to extreme temperatures could lead to top-down effects on plants, where certain plants that are out in more extreme conditions are allowed to continue to grow because deer are forced to browse and feed in thermal refuges, and so the plants within those thermal refuges may get hammered a little bit more than those out in the open. Of course, thermal selection could lead to novel predator-prey interactions. If deer are forced into areas of thermal refuge and predators are able to key in on those changes in space use, this could have significant impacts on predator-prey interactions. And then finally, there may be trophic cascades or even ecosystem shifts. And this is kind of a framework here that suggests that as habitat fragmentation facilitates edge effects, we could expect that changes in temperature associated with those edge effects influences the thermosensitivity of individuals, which leads to changes in population processes, which then ultimately affects the species and the community of a landscape, which could lead to fundamental ecosystem changes and community shifts in those ecosystems. So this is an area of research that is growing, and hopefully we gain more knowledge in that. And finally, I just want to kind of finish up with kind of a global perspective, a global change perspective. Of course, we know in Texas and in much of the eastern United States, population and housing density is increasing quite a bit. This is going to have direct impacts on our natural landscapes and natural rangelands in which deer inhabit throughout their distribution. It's going to increase fragmentation, and coupled with that increased vegetation fragmentation is, of course, predicted increases in extreme temperatures in the next 50 to 100 years. This is some models showing predicted number of days over 100 degrees Fahrenheit up till the year 2060. And so we can see that in much of Texas, and especially in South Texas, we're predicted to get some really long hot periods. And so when we think about not only habitat fragmentation, but then coupled with increased in temperature extremes, we can kind of picture this in a framework that says, okay, we need to start to understand how breaking up vegetation, reducing thermal options for organisms, and relating that back to their performance curves, how this is going to have population level and management implications for these organisms going into the future. So I guess the take-home message here is, let's think about all of this from a management perspective. Thermal heterogeneity is common in landscapes. It's often large and predictable, and management can directly influence temperature. I hope I've proved this now by showing how vegetation moderates temperature. Here's another example, if we need it, showing variability in daily ranges of temperature between 3 different vegetation types. Or even here, where we start to look at how clear cuts and group selection of forests fundamentally change the thermal landscape compared to controlled areas. So we really need to think about how thermal cover is truly a part of habitat, and that cover is not just escape cover. It's not just predator avoidance cover. It actually functions to moderate thermal conditions for organisms. Mechanisms that influence the thermal variation is still largely unknown, and we're starting to build on that knowledge with some of this research I'm presenting today. And really, we need to think about variability and heterogeneity of vegetation in landscapes as kind of a hedge for these extreme weather conditions. Homogeneity is not a good thing when it comes to thermal conditions, because then we limit the thermal options during this extreme periods for organisms, which can translate to population crashes. And then finally, I hope I've shown that temperature not only has direct implications on physiology, movement, space use of deer and organisms in general, but that our understanding of cover in the past and even space use has been relatively naive with relation to thermal ecology. And so really what I hope you take home from this is that if you're looking to manage for deer populations, not only just in Texas but throughout their distribution, that you think about how those management actions impact the thermal options in the thermal landscape for deer and organisms within your system. I thank you for your time. I thank you for listening to my presentation, and I look forward to answering any questions you may have.